Let us see how to derive the stiffness matrix of a CST element. We will use the minimum potential energy theorem to derive the stiffness matrix. We will derive an expression of the form Ku is equal to F, where U is the nodal displacement vector. U1, V1, U2, V2 and U3, V3 are shown in the constant strain triangle element. F is the nodal force vector, that is, if the x component of the force acting at the node 1 is F1x and at node 1 the y component is F1y, and at the node 2 the components of the force are F2x and F2y and F3x and F3y at the node 3, then we can write the nodal force vector F as F1x, F1y, F2x, F2y and F3x and F3y. So in the expression we have on the right hand side the nodal force vector, and K is the stiffness matrix of the element given. Also U has 6 elements, also F has 6 elements, therefore K, the stiffness matrix, would be a 6 by 6 matrix. I will first qualitatively explain the minimum potential energy theorem. Let us consider a spring and imagine that we attach a force at the end of the spring or a mass. So the spring will elongate, and let us say that the displacement at the end of the spring is delta. Imagine that we are going to attach the mass at the end and just drop it. What will happen is that the spring will initially oscillate, the mass going up and down, or the end of the spring is at different positions, or we can say that the displacement can take different values during that time. Finally, what will happen is that the spring will come to a rest at its equilibrium position. Now let us see the minimum potential energy theorem. Out of all the displacement configurations means these different values of delta that it can take. Out of all the displacement configurations that a body can assume, the displacement configuration at the equilibrium, that is at the equilibrium, which is delta, corresponds to minimum potential energy. What it says is that if you are able to calculate the potential energy pi of the spring, then when this is at equilibrium, which corresponds to a displacement delta, then the potential energy that we calculate will be a minimum value. If we assume the delta to be more than this delta, then we get a potential energy value which is greater than this value. Therefore, this theorem will help us to find the value of the delta. The only thing that we have to do is just find the delta, which will give you a minimum value of the potential energy. Now let us see what this potential energy is. The potential energy of the spring comes from two factors. One is because it is being stretched. Because of that, we would have a stored elastic potential energy. And we also know that this stored elastic potential energy is nothing but the elastic strain energy of the spring. The next component of the potential energy comes from the applied force. Here the force corresponding to this mass m would be F is equal to mg, and we know that the displacement is delta. So, force is F and the displacement is delta. So, the magnitude of the potential energy because of the applied force is the work done, and we know that work done is equal to the force into displacement. But you also have to consider that we have already used this force to do some work. So, we can say that the potential of this force to do work is lost. So, this quantity is considered as a loss in potential. Therefore, we give a minus sign to this work done to denote the loss in potential. Also, we will call this as the work potential. So, total potential energy is equal to strain energy plus work potential. We use a notation pi for the potential energy, and so pi is equal to the strain energy U plus work potential, let me write it as Wp. Also remember that the work potential is a loss in potential, so therefore this quantity will be negative. For the spring, if K is the spring constant, then the strain energy U is half K delta square, and the work potential would be minus F into delta. So, this is pi for the spring that we have considered. What we have to now do is to obtain the total potential energy for the constant strain triangle element. For calculating the strain energy, we require stresses and strains. The constant strain triangle is a 2D or a two-dimensional element, so it can either be in a plane stress or a plane strain state. For both these states, the stresses and strains are sigma x, sigma y and tau xy, and epsilon x, epsilon y and gamma xy respectively. Let me also write the strain displacement relation, that is epsilon is equal to the strain displacement matrix B into the nodal displacement vector, and the stresses and strains are related as sigma is equal to the material property matrix D into the strain epsilon. Here I am using the curly braces to represent that this is a 3-element column vector. This is also a column vector. This is a matrix. D is a matrix. Now the sigma I can write as sigma is equal to D into epsilon. I can substitute with B into U. Also during the derivation, I will use epsilon transpose, which will give you a row vector. So epsilon transpose is epsilon x, epsilon y and gamma xy. You should notice that by default we write a vector in the form of a column vector. So if you want a row vector, our convention is to just take the transpose of the column vector. So when you see these kind of annotation, remember that this is just the row vector form. We will use these expressions which I have written to calculate the strain energy. The strain energy per unit volume, small u, is equal to half into epsilon x sigma x plus epsilon y sigma y plus gamma xy tau xy for a 2D case. We can write that as a product of two vectors. So this would be equal to half into epsilon x into sigma x plus epsilon y sigma y plus gamma xy into tau xy. We have seen that this you can write as epsilon transpose and this is sigma. So this equation can again be written in a compact form as half into epsilon transpose into sigma. This is strain energy per unit volume. Remember that sigma is equal to d into b into u, so we can substitute this term. Also, epsilon is equal to b into u, which will give epsilon transpose as u transpose b transpose. If you have product of two matrices A and B, and if you want to take the transpose of A into B, this would be equal to B transpose into A transpose. This is what I've used in this expression. What I will do now is I'll substitute sigma from this equation, substitute epsilon transpose using this expression. So this is equal to half into u transpose b transpose, and we'll substitute sigma from this equation. This into d b u. The strain energy capital U can be written as integral over the volume half u transpose b transpose dbu dv. From this equation, I'll take half outside the integral. I can also take u transpose outside the integral and this u outside the integral, because you know that u is the nodal displacement values and it does not change with position. Therefore, I'll write half u I have taken outside and then the integral over the volume b transpose db, and then this u also I'll take outside the integral sign. So then dv and then multiplied by u. If you remember, D is a 3 by 3 matrix, B is a 3 by 6 matrix, and B transpose would be a 6 by 3 matrix. And when you multiply these three, what you will get is a 6 by 6 matrix. What I'll do is I'll substitute what is inside this bracket with a matrix K as this, so that my equation looks compact. So u is equal to half u transpose K into u. So we have the expression for strain energy. Our next step is to find an expression for the work potential. For getting an expression for the work potential, we require the displacements u1, v1, u2, v2 and u3, v3, which are the displacement values at the nodes 1, 2 and 3. We also require the forces at the nodes 1, 2 and 3, and we can multiply the displacements with forces to get the work potential. And the forces at node 1, 2 and 3 are F1x, F1y, F2x, F2y and F3x and F3y. So we have the nodal force vector over here. The work potential can be written as the product of forces and displacements, and it is a negative value. So minus of, we can write F1x u1 plus F1y v1 plus F2x u2 plus F2y v2 plus F3x u3 plus F3y v3. That is, just you multiply the force F1x with the displacement there, which is u1, F1y into v1, F2x into u2, F2y into v2, and so on. In compact form, I can write this as minus of u transpose F. When you take u transpose, this becomes a row vector and F is again a column vector. So how do you multiply them? Is you take the dot product as u1 into f1x plus v1 into f1y plus u2 f2x, v2 f2y plus u3 f3x and plus v3 f3y. So you get the same thing. Now we can substitute the values of strain energy and work potential in the equation to calculate the total potential energy. Therefore, finally we get the total potential energy pi is equal to half u transpose into k into u minus u transpose F. Now, what the minimum potential energy theorem states is that we have to find the nodal displacement values u1, v1, u2, v2 and u3, v3 in such a way that the total potential energy is a minimum. To obtain u for minimum values of pi, what we have to do is we have to differentiate pi with respect to u1 and put it as a 0 value. Also differentiate it with respect to v1 and equate it to 0. Also for other values of nodal displacements. Now, when you differentiate this pi with respect to u, what will happen to this is this u term will go. That is, if you differentiate dou by dou u1 of f1 u1, what you are going to get is f1. That is, when you differentiate, you will lose this u term. The same thing will happen here. When you differentiate pi with respect to u, the u term will go. Again, this should happen with this u term also. So this u transpose term will go. Also, if you see, there is a u term here and there is another u term here. So when you multiply these two, what you are going to get is a quadratic form or a u square form. And you know that if you differentiate u square with u, what you are going to get is 2u, or there is a term 2 here. So that 2 term which appears after differentiation will cancel with this 2. So in effect, what you are going to lose is this as well as this when the left hand side is differentiated and equated to 0. So you will get 0 is equal to k u minus f. The thing is that I have taken only one of the terms from either of these and tried to explain what is going to happen in a qualitative way for you to have a sense of what happens during the differentiation. Therefore, finally, we get the expression k into u is equal to f. So we have derived the expression of the form force is equal to stiffness into displacement. Therefore, this k is our stiffness matrix. Therefore, to find the stiffness matrix, what we can do is we can integrate B transpose dB over the volume. Even though we have derived this for a 2D element, this can be also used in the case of a 1D element, one-dimensional element, or a bar element. In that case, the D matrix will be a single value, which is the Young's modulus E, And you also know that the B matrix will then become a vector of 2 elements. For two-dimensional case, the D matrix will contain 2 material property values, which are Young's modulus E and the Poisson's ratio nu. Now, if they are constant over the volume, then we can take this product outside the integral sign and write B transpose dB integral dV, and this quantity, you know, it is the volume itself. So, I will write this as B transpose dB into V subscript E. V subscript E stands for V volume of the element, E stands for element, and to calculate the volume of the element, what you can do is we can multiply the area of the element into the thickness T. So, for evaluating the stiffness matrix while doing problems, you can use this expression. We will stop the video here, and in the next video we will do a small example problem.